The experiment 8 and 11, standard retention times and GC data analysis, okay? You want to make sure that you have assigned identities to all the peaks that you can assign, okay? So just be careful when you are doing that analysis. If you come across something you don't know, just make sure that it really truly is unknown. So like I was talking about last week, like all the alkenes, we don't have standards for every possible alkene that you guys could have made. We have 6 different ones, 3 heptenes, 3 octenes, and we've shown you trends in positionally where that double bond is and how retention times vary with cis versus trans, okay? So make sure that you use that information to help you identify all your alkenes. So the heptenes are in the mid-2s or so, 2 minutes. The octenes are in the 4-minute range. If you have a peak that's in that range, but you haven't identified it, that more than likely it probably is some sort of alkene, so you need to figure out, give a best proposal for what it is, even if it doesn't fall on the standard retention times, okay? Another thing that's not on there is potential ketones. So it's possible that you oxidized your alcohol at some point and made the ketone. Those ketones come slightly before the alcohols. They are not on the standard retention times, but you've got to remember to assign identity if you think that you have ketones, okay? So just be really careful in your analysis of the GC data. Anything you don't know what it is, you're going to assign unknown, but make sure you truly don't know what it is before you assign it to be an unknown, all right? Okay, experiment 12, we are looking at, so have you guys covered elimination yet? We got there? Okay. We're about, and was that Friday? Yeah. Okay, we're about that far ahead on our next reaction, all right? So this week, in experiment 12, we're going to do what is called a Diels-Alder reaction. And it's a capital D and a capital A. Two people discovered this reaction. Otto Diels and Kurt Alder in 1928 figured out this reaction. In 1950, they got the Nobel Prize for it, okay? And it really is a really powerful reaction. You will get 2 carbon bonds out of this, so that's a pretty good deal for, pretty good value for your organic reaction money. And I'm going to go through all the different features that it holds together as far as what you are able to make with the reaction, which includes also a ring with a double bond in it, so you are allowed another piece that you can then functionalize with something else because you can add on to that double bond. So this is a really powerful reaction, and it's used in multiple different arenas, okay? It's used in drug design, it's used in industry, it's used in all sorts of different arenas because it is so powerful. So it's kind of like the Grignard reaction. If you can set it up just right so it works really well, then people are going to use it, all right? And so I'm going to go through kind of the basics of it, but I'm not going to probably go through in detail like you're going to get in lecture, but you'll get all that information again in lecture, okay? So this will be kind of round 1 of making you familiar with it, and then hopefully with reinforcement of what you're covering in lecture, you'll have it down by then, all right? Basically, what is involved in a Diels-Alder reaction is there are 2 pieces. There is a diene and there's a dienophile, and we're going to talk about those 2 pieces here in a little bit. Okay? So we've got a diene and a dienophile. So the diene is what it says it is. It's got 2 double bonds instead of just 1 double bond, all right? And the dienophile wants to react with that diene, all right? And what you get out of it is then, like I said, you get a ring, and you get a double bond in that ring, so then you're able to do more chemistry with that ring. So you've made a ring, you've made 2 carbon-carbon bonds, and you've got a position where you can have more chemistry done on what you've made. So that's a pretty good deal out of the whole thing. What is key to this whole reaction working is how the p orbitals of our double bonds interact and how they end up overlapping, okay? And you guys are going to probably in more detail talk about what energy levels these p orbitals are at and where things are positioned and so forth. But it's the p orbitals that are interacting, and they are then helping us to have this reaction occur, okay? So here's an example down here of that reaction. If we had 1,3-butadiene, and then we reacted with our diester here, ene diester, then this is which is also known as a malonate. This is the product that you would get. And another key to it, we're showing stereochemistry here because that is something that is conserved throughout this reaction, right? So the Diels-Alder reaction is known by a couple terms, okay? It's a concerted mechanism. So what that means is you've got it happening in a single step. Maybe it'll look like 2 words here. Or 1 word, it's 2 words. It's happening in a single step, and you've got a cyclic transition state. We don't have an intermediate here. We just have a transition state. We've got our concerted mechanism. It's cyclic redistribution of electrons. We've got a pericyclic mechanism, so that brings into the fact that it's the cyclic transition state. We've got what's called a 4+2 cycloaddition. So our 4, 1, 2, 3, 4 plus 2 cycloaddition. We're putting the 2 together and we're getting a ring out of it, all right? And it's neither polar or a radical mechanism, okay? So you've got this orbital overlap, you've got the sigma overlap of your p orbitals, and it's that head-on, the 2 pieces coming together, they overlap, and then from that we get this redistribution of electrons that then forms the ring that also includes a double bond in it, all right? Now for the diene and the dienophile. The diene, it needs what's called an S-cis conformation, okay? And what that does is that brings the diene in that conformation versus trans would be like that, all right? And what you want is you want your 1 and 4 coming together like that so that they can react with the dienophile. You want them here so they can come together and react with these 2 carbons. If you got one of them flipped back, you're not going to get good orbital overlap for the reaction to occur, okay? For the dienophile, you want to make it so it wants to react with this diene. Yep.
Can't they just interchange between them since they can rotate around the single bond, single carbon?
Well, if you think about it with this diene, it's kind of like an aromatic ring. It's not, you know, it's kind of a partial double bond all the way throughout. So it's not like it's just going to freely rotate, okay? And this reaction happens so quickly and instantaneously when it works out well that if you don't have it set up like this, it's not going to react. If you're flipped the wrong direction, it just won't react. It's not going to like have one side react and the other side find itself. It just won't happen because the 2 of them have to be lined up together for it to react all at Now for the dienophile, you want the dienophile to want to react with a diene. So if you want something to react with something that has 2 double bonds, you want it to have electron donating groups or electron withdrawing groups? Because you've already got some extra electrons here, right? So you want to make it so it's got extra, it has electron withdrawing groups on it, pulling some of that electron density away from the alkene, make it more reactive, okay? So you want to make sure you have some electron withdrawing groups on there to make it reactive, okay? And so like examples would be, if we just had ethylene, that is not very reactive in a Diels-Alder reaction. But if you even just add an aldehyde on one side, even that is enough to make it reactive. Or if you made this, then instead of an aldehyde, put an ester on there. These two are both going to be much more reactive in a Diels-Alder reaction than this guy is, because you pulled, with these electron withdrawing groups, you're pulling some of that electron density away, making it so these carbons then want to react with that diene, all right? So those are kind of the 2 keys for the reaction. We have to have the S-cis conformation, so we can have the 1 and 4 carbon able to go through that cyclic transition state together. And then we want electron withdrawing groups on our dienophile. That'll make it much more reactive, right? Now, talk about this part here. With the Diels-Alder reaction, your stereochemistry is conserved. So that is really important as well, because you're not going to change your chiral centers with the stereochemistry. That stereochemistry is conserved, right? You also, you also make what is called Endo Product, but you don't make Exo Product. So what that means, if you've got your diene and dienophile are lined up together, we've got good orbital overlap of our diene and our dienophile coming together, then the product that is formed directly from that is the endo product, okay? So these two coming together, then we would make our endo product. If we don't have a good match, what you would get is the exo product, but that doesn't form because you don't have good orbital overlap. So you have to have good overlap to get the reaction to work, okay? So you make endo product, not exo product, all right? So again, something else you'll probably touch on in lecture, but you've heard it once now, and then it'll come back around a second time, okay? But endo product is what you make with the Diels-Alder reaction. So our specific reaction that we are going to do is we are going to take cyclopentadiene. So cyclopentadiene, here's 1, 2, 3, 4. Here's our 4 carbon, okay? And we've got N-phenylmalamide, okay? So here's the structure of it. Here is the alkene that's being reacted, or the dienophile, all right? So we've got this in S-cis, right? Because cyclopentadiene holds it in the S-cis conformation. And then here, we've got actually 2 electron withdrawing groups. We've got the imide, IMIDE, okay? That's this functional group. And because of it, we've got an electron withdrawing group here and an electron withdrawing group here, okay? So it's making the dienophile very reactive, all right? And you'll find that this week, like your reaction will go lickety-split. Like you will actually visually be able to see it go, because this is bright yellow, and so you'll have a yellow solution, and then all of a sudden it won't be yellow anymore, and that's how quickly it'll react, okay? So electrons flow around our cyclic transition state, okay? So we've got from carbon 6 to carbon 1 here, we've got this double bond, so we've got electrons flowing here, and then electrons from this double bond flowing here, electrons flowing here to make this bond, okay? So we've got 1, 2, 3 is how those bonds, we're moving this bond and we're making those two bonds, all right? Does everyone see that? So 6 and 1, and then between 1 and 2 goes to between 2 and 3, between 3 and 4 bonds over here with 5, all right? And so then, like I said, we get the endo product. So for this case, to have our cyclopentadiene and N-phenolmalamide to react, we get this product, which is, if you imagine kind of my hands together, here's the cyclopentadiene and N-phenolmalamide coming together best they can, versus this way, we'd have things pointing a different direction, right? So we get our endo product. We also, here's where we conserve our stereochemistry, okay? So where these protons are, that helps us conserve the stereochemistry, right? Now, to get cyclopentadiene, you can't just buy cyclopentadiene. It doesn't exist as just cyclopentadiene. It actually likes to react with itself. So it, as a diene, also works well as a dienophile, okay? So it reacts really well by itself and becomes dicyclopentadiene, all right? So to get the cyclopentadiene, what we've got to do is what's called cracking. And that cracking is a retro Diels-Alder reaction. So we're going the other direction. We're taking what is a Diels-Alder product and we're going backwards and breaking it into its two pieces, all right? So this week in lab, before you start the lab, I've got to, it doesn't stick around really well as cyclopentadiene. It has to happen right before you start the lab. So this week in lab, right before the 7:30 labs and right before the 1 o'clock labs, I'm cracking the cyclopentadiene, and you're going to get this from your lab prof, okay? They will give you, it tells you in your lab man, you need 0.6 milliliters, so we're going to deliver to your reaction with a syringe that cyclopentadiene, okay? Because even after it's been cracked, we've got to keep it cold on ice to keep it as cyclopentadiene before it reacts with your dienophile in your reaction, all right? So you will get your cyclopentadiene from your lab prof after it's been freshly cracked, okay? And then, like I said, this reaction takes place very quickly, okay? So what you're going to do is you're going to have the solvent for the reaction is ethyl acetate. You will have your N-phenolmalamide dissolved in the ethyl acetate, okay? And you will come see us, and we will give you the cyclopentadiene, all right? If your solid does not dissolve, you most likely use the eluent for TLC. So I'm going to talk about that here in a minute. But the eluent for the TLC is 1:1 hexane to ethyl acetate. It will not dissolve your yellow solid, all right? So if your yellow solid will not dissolve, you've used the wrong thing most likely. It will only dissolve in straight ethyl acetate, all right? So watch labels because they look very, very similar to each other. ethyl acetate versus 1-to-1 hexane to ethyl acetate. All right? So after they are added, we're going to reflux it for all of 10 minutes. That's how quick things go. You'll cool things down. You're going to precipitate out your product with hexane after you distill off the ethyl acetate. So you'll reflux, distill off ethyl acetate, precipitate your solid with hexane, and then you'll recrystallize it with ethanol. And this is a really nice reaction because in the end you get nice, beautiful white solid at the end. Okay, so it'll look like a product should. Nice pretty crystals, nice white, solid. All right. For that product, you're going to want to collect the yield. In a little bit here, I'm going to talk to you about TLC and layer chromatography. So you'll analyze it with TLC. You're going to collect the IR spectrum. It's a solid, so you'll collect it just like you did with polystyrene, where you put background amvils up, and then for the solid, the amvils down. Don't crank on the back side of the IRs. I've had people having trouble collecting their IR spectra because the anvil height has been changed. We don't want to change the height. They're set just where they are supposed to be, and if you change the height, you don't get a good spectrum. Okay? So IR of a solid, and then we will also collect the melting point. There is not a standard to compare it to. You're going to collect the melting point of the solid. Okay? So this is going to be the analysis for your product. Yield, TLC, IR, and melting point. All right? In a little bit, here I'll give you some more information about the product. Okay? All right, so questions on that? Okay. The reaction and the procedure and the workup, all of that is pretty straightforward this week, okay? And pretty quick to happen. The thing that'll be a little less straightforward is that we're going to use thin layer chromatography, okay? So, thin layer chromatography here we go with our third chromatography. So what does chromatography tell you? What is it? What are we doing? We're doing some sort of separation, right? Because that's what's involved with chromatography, okay? It's also known as TLC, all right? It separates things best based off of polarity. So you've got separations based on polarity. So with chromatography, what are the two pieces we always have? Stationary phase, mobile phase, okay? Your stationary phase is some sort of adsorbent, okay? And I'll talk about that here in a second. On like some sort of support. And what I mean by support is it's usually either on polystyrene, which is what we have. Our TLC plates are on, the silica's on plastic, or it could be on foil, like aluminum, not just aluminum foil, but a little thicker aluminum backing, or they could be on glass, okay? So the ones we're using are on polystyrene, so they're kind of flexible, so you have to be careful not to flick all the silica off of them, okay? So we've got a stationary adsorbent on a support. Our adsorbent is silica. Another common one is alumina, which we won't be using, okay? So ours is silica, all right? So our stationary phase, got a word there, okay? Our mobile phase is our solvent or our eluent. So get used to using the term eluent because that's kind of more accepted way that you discuss thin layer chromatography is the eluent or the solvent, okay? So what happens with thin layer chromatography is you've got this TLC plate, which we'll show you the plates in lab this week. This isn't the greatest picture of it, okay? But we've got this plate. It has silica on it. We already have lines even drawn on the bottom, so they don't come with lines drawn on them. You usually have to draw them on, but we've done it for you, okay? So there's a line where you're going to take capillaries, so we're going to teach you how to pull capillaries, and you're going to spot different things on the bottom of those TLC plates, okay? And the reason you want the line is because you want to spot them on at the same level on that TLC plate, okay? I'll show you in a minute here how we measure things, so it's important that everything's on the same level, all right? And then what you do is after you've spotted your TLC plate, then you're going to put it in a developing chamber, okay? And the eluent, the solvent, is in that chamber. What happens is that solvent's going to travel up the TLC plate, and as it does, it's going to catch whatever's spotted on the bottom, and it is going to travel with the eluent up that plate, and then when you're done, you'll somehow be able to visualize spots on that plate to see how things have separated and how they've traveled, okay? Now what's going on is there's this equilibrium between being absorbed in this stationary phase so it's either absorbed on stationary phase or it is traveling with the eluent, okay? All right? Now, silica is something, it's fairly polar, okay? So if we're looking at the separation is based on polarity, okay? Silica is fairly polar. Where do you think the polar compounds hang out? With the silica, right? Okay? Versus things that are more non-polar hang out with the eluent, all right? So if you hang out with the silica, you don't travel very far up the plate. If you hang out with the eluent more, because it's more non-polar, it travels farther up the plate, all right? So that's how you can tell the separation. More polar things won't go as far, less polar things will travel farther. Yeah?
What is the difference between adsorbent and absorbent?
Adsorbent has to do with the process of it actually interacting with the silica, and that's called adsorbing, just as absorbing. So it's not absorbing to the silica and staying with there, it's still going back and forth. Still, even though it wants to hang with the silica more, it's still doing this back and forth. It's just hanging over here more than over here. Yeah?
Sorry, did you say polar or non-polar travels farther?
Non-polar travels farther. So when you think about like kind of the rules of polar versus non-polar interactions, like hangs out with like, right? So things that are more polar are going to want to hang out with silica. Things that are less polar won't hang out with the silica as much and travel with the eluent, right? So what we're going to do is we're going to try and monitor our reaction with TLC and see how it progresses, all right? And so here's kind of an example. If we had, so these are different unique spots, okay? So here's what is called our origin line, all right? So if we had a reactant A and a reaction mixture B and then a known product standard C, the reactant and the known product standard are things we can spot on the TLC plate, and they won't change in what is going on. The reaction mixture, as it progresses, will change, okay? So like here at time 0, what's in that reaction mixture is all reactant because it has the same, it's traveled the same amount as the reactant standard, okay? In between time, we've got some reactant and some product, and eventually as the reaction progresses, all our reactant goes away for that middle lane, and we only have product, okay? So we're going to be looking at the same thing with your reaction, but your reaction is so fast that you will be TLC in your as soon as we add the cyclopentadiene, we're going to tell you, have your TLC plate ready, have your spotters ready. You're going to spot that reaction because it goes so quickly. If you don't spot it immediately, it will be over before you can actually catch it, okay? But we're going to look for this similar type of progression, okay? Now things that we are looking for with TLC, okay? So we have I've talked about our origin line, that's where we spot on our TLC plate, okay? What we've done is we've drawn it 1 centimeter up from the bottom of your TLC plate so you have plenty of room to spot on it and still get it in the chamber without the eluent being above that line. You don't want the eluent, when you stick it in the chamber, you don't want the eluent above it. You want it to climb up it, okay? And so you want to make sure that eluent is below that origin line. Then once you develop it, you're going to let that eluent travel up to the top, and you want to stop probably about 1 centimeter from the top. You'll pull your TLC plate out of the chamber, mark that origin line, and then you're going to look and see what spots you have, okay? There's multiple ways you can visualize what's going on with a TLC plate. We are going to use UV light, all right? Now, what do you know about aromatic compounds and UV activity? Are they active or not? They are UV active, okay? So that's how we can see them. So it's kind of a key with our dienophile is it has that aromatic ring on it. That's what makes it so we can see it as a reactant and see it as the product. We've got that aromatic ring all the way through to be able to visualize it, okay? The TLC plates have a fluorescent dye on them so that when you develop it and let the eluent dry and then stick it under a UV lamp, you can see things will be kind of dyed kind of a purplish color so that you can see those UV active spots, okay? So say this is a TLC plate we've developed and we've got spots on it. We now need to characterize the spots. And the way we do that is what is called an RF value, okay? So the RF value is the distance from the origin traveled by the compound divided by the distance from the origin traveled by the solvent, okay? So remember, our origin is here where we drew that line. So it's the distance traveled by the compound, so from here to here, for example, for A, divided by the distance traveled from the origin all the way to the solvent line. Those are the two measurements that you're making, all right? And so like for A, it appears that it, like based on this information, it's 7 millimeters divided by 50 millimeters. You've got RF value of 0.14, okay? So since you have a distance divided by a distance, our units cancel out, and RF values don't have units. They're just numbers, okay? Now we talked about polarity, relative polarity with the TLC plates. One thing that's key with TLC plates is you're not going to make an eluent so polar that you're going to become more polar than the silica. There's not really a usable eluent that is going to become more polar than the silica, because usually what will happen is it'll actually dissolve your silica, okay? So you will never have like solvent, your spot is going to outrun your solvent or stay right with your solvent, okay? It's always going to be at least a little bit less polar. So RF values will always be less than 1, all right? Because the spots will stay below the eluent. You're not going to flip that, okay? You're not going to outrun it, all right? So RF values are always less than 1, and we've got units divided by units, so there's no units on the RF values, all right? Okay, questions about measuring those? Any questions? Okay, let's go through some examples here. Okay. Okay, TLC plates, when you look at them vertically, not sideways. Okay, they only make sense with the origin line on the bottom and then the top of the plate above it. Okay, they don't make sense when they are sideways. All right. Okay, let's say we have 2 points here, A and B, okay, and we have our origin line here. All right. Let's say this origin line is 5 centimeters. All right. And we've got A that's traveled 3.5 centimeters. So what would be the RF value for A? What numbers would you use?
45 over.
It'd be 3.5 divided by 5. Okay? And then you'd calculate that to its decimal, right? So basically be 0.7. Okay? So similarly, if B is here and it's 2 centimeters, what would be the RF value for B? What numbers would you use? 2 centimeters divided by 5 centimeters, right? Because this number is the same, 5 centimeters is the same for either spot, okay? All right, so looking at this TLC plate, what is the less polar spot? A is the less polar spot, right? It traveled more with the eluent and hung out less with the silica. So this is less polar, B is more polar. Everyone good with that? Okay. What if we wanted, so say we used 1:1 hexane ethyl acetate for this. Okay? What if we wanted those spots to travel farther up the plate? How would we change our eluent? Would we want to make it more polar or less polar?
More polar.
So you want it to travel farther up the plate. You want your spots to hang out, your compounds to hang out more with the eluent. So would you make it less polar or more polar? More polar, right? So you want to go to something like, which of these two is the more polar solvents, hexane or ethyl acetate? Ethyl acetate is more polar than hexane, right? So you would want to do something like 1:3 hexane ethyl acetate. That'll make those spots travel farther up the plate, have greater RF values. Okay? And usually with TLC, you don't have, like, you usually don't develop compounds in just hexane, or usually not just ethyl acetate. You have a combination of a nonpolar and a polar solvent to help with the polarity of whatever you are looking at. Yeah.
Can you explain that?
So, in order to make the spots want to travel farther, they want to hang out with the solvent more. And so, in order to hang out with the solvent more, that solvent needs to become more polar to help it move farther up the plate.
I thought non-polar things move farther.
They would, right? Like this did move farther, but if you want it to move, this is the compound versus talking about the eluent. So to actually get the compound to move farther, you need a more polar solvent. Okay? So you got to increase the polarity to get things to move. Okay, so let's look at opposite case. If we wanted to slow it down, we decide those RF values are too large. What would we do? What would we change the polarity to? We'd make it less polar, right? So then, if we wanted to slow down, we'd change it to where we have more hexane and less ethyl acetate. Okay? So you're kind of looking at two different things. You're looking at what that solvent can do to those spots and what's actually happening with the spots. Okay? Now, when you make measurements, you're measuring usually from the center of the spot. Okay? Because our value for a given solvent or a given system, RF values are consistent for that system, okay? So for this week, we'll have a product standard, we'll have a starting material standard, and you'll have your reaction, and you're using 1-to-1 hexane ethyl acetate. Each time you develop a TLC plate, the RF values should be fairly consistent with each other because it's a consistent system, okay? But if you change what the eluent is, then you've changed what those RF values are going to be. All right? Now for this week, there's at least, your instructor may give you more spots that you'll need to develop, but there's at least 3 times you're going to look at TLC of what's going on, okay? So you're going to spot your reaction at time 0. That's right when that cyclopentadiene is added to your reaction, okay? You're going to spot it at time equals 10 minutes. So that is after the 10-minute reflux, okay? And then you're also going to spot it when you have your final product. When you spot a TLC plate, you can only spot things that are in solution. So you can't spot, if it's a liquid, like a neat liquid, like say you wanted to spot your alcohol or alkene from the previous experiments, you still need it dissolved in a solvent, okay? So here we've got what you're interested in dissolved in a solvent, right? Because it's a reaction in ethyl acetate, all right? When you get down here, you're going to need to dissolve that final product in a little bit of ethyl acetate to be able to spot it on a TLC plate, okay? You probably will not put this all on one TLC plate. You will probably use multiple TLC plates, so your instructor will tell you what they want you to do. And also keep in mind, you'll also be spotting with your standards. We've got a reactant standard and a product standard, okay? So there'll be more than just these 3 spots involved. Each time you develop a TLC plate, you're going to put these 2 on there as well, all right? And usually what you will do is kind of like that example I showed you a couple minutes ago. You will usually put your standards on the outside, so say this was the reactant standard, product standard, and then you put what experimentally the spots that you're interested in. So for example, if we do time 0 and time 10 minutes, you put your standards on the outside and the spots you're trying to evaluate, analyze in the center. Or you may do reactant and product in just time 0 and then put time 10 minutes with the final product, something like that is a possibility too. So find out from your lab prof what they want you to do. When you record TLC plates in your notebook, you record them vertically, you draw them vertically, okay, and you record them life size. So you want them exactly the size of what they are in real life. Typically, with a research notebook, you would probably tape them in. However, we don't want you transporting TLC plates back and forth. So most likely your lab prof's going to have you draw vertically, life-size, what your TLC plate looks like. Put all the measurements for your RF values on there, and either keep your TLC plates in your lab drawer or dispose of them in glass waste, because they're silica, so they go in the glass waste. Okay. For this lab, you have a report sheet that you'll be filling in. Okay. So the first part, you have all your information about your product. Everyone should be making the same product, so it's not like the unknowns where everyone's different. Everyone should draw the same structure here. You've got your name, give the melting point range of your product, your yield, your percent yield, date, so on and so forth. And then, and what does that product look like? Then you're going to show your TLC plates on this sheet as well. So you'll have them in your notebook, and then on this sheet, you want to give, for whatever your spot A ends up being, tell us what that is, and then give us, if you have a spot in spot A, what is its RF value, or if you have multiple spots, what are the RF values, okay? So you have a description for a spot and the RF values, okay? And you only fill out as many TLC plates as you actually develop. So a lot of you won't need the third plate. A lot of you will be done with just 2 plates, all right? So you'll fill out this information for the TLC plates, okay? With TLC, if you have 1 spot, that means that that compound is pure, okay? So if it's by TLC looks like it's 1 spot, you would say it's pure by TLC. Now sometimes that gets a little iffy if you've got something that's compounds that are going to overlap. We've set it up this week that 1 spot should mean purity. So if you have a product spot and it's the only spot in, you know, say you spot it in lane B, your product is pure by TLC. Now keep in mind we're looking at it with UV, so if we can't see impurities with UV, we can't see them. So that's why you put the disclaimer on it. 1 spot is pure by UV activity, okay? On the back side of your report sheet, you're going to fill out your information for your Experiment 12 products IR. On Moodle, I will also post the standard IR spectrum for cyclopentadiene, for N-phenylmalamide, and the standard product for Experiment 12. And then you will also attach a conclusion to this, okay? So your lab profs will tell you specifically what you need for that. Finally, I told you I'd give you some information to help you out with Prelab for this lab. So here's some information about cyclopentadiene and phenylmalamide, and then here's the information about your product. Your product doesn't have a name because it's unique to our experiment, but here is its formula, its molecular weight, and then here is its melting point, okay? So I'll give you all that information to help you with your Prelab.